We'll come back to joint order statistics today. Also, we're going to try to figure out from this the joint distribution of the range and the mid-range. We did study that problem and look at it in that original example where xi was coming from a uniform 0, and I'm going to change my parameter to alpha because that's what they're using in the book. That's what I used in my code. I usually like to think about theta, but alpha is theta in this case. It's the unknown parameter. What we really want to do is just figure out this joint distribution. I think it's a good example. It keeps coming up. There's interesting artifacts about this example. That the parameter is on the boundary of the space. So later on we'll reconfront this and see. It's very difficult to see what the very best estimator is, but we still have been coming up with principles on what are good estimators. So one thing we should at least be inclined to believe is that a good estimator would involve the max order statistic for alpha. That is the thing that appears in the likelihood function. We'll be more formal about that in chapter 6. So we'll do a little bit of joint transformations. I'm also going to give you new homework probably on Friday or Monday, and I'll give you some transformation problems to play around with. So I think we're still in the review period with chapter 5, learning about probability distributions and motivating for inference. So I will give you some of these. I'll be asking you questions just as a reminder, like where does the Jacobian come from? What is that? And if you didn't understand what that formula is, there's a couple of those homework problems that could really help us to understand where those formulas come from. In review session, I tried to expound on all of that and let you know and try to come up with here's how you do this in general and here's where the Jacobian comes from. If you guys ever want to review on any of that stuff, that's fair game for review session. So if you're like, please give me an undergrad lecture on this stuff and scale it up to the grad school level. So sometimes we miss things in classes where it's like, surprise, now we're doing it all in multi-dimension and we never really thought about it. So just a note, we'll do review on Wednesday, this Wednesday at 5:30. And the review session is here. Like right here. So anyway, so whatever this room is, what are we in? 409 or 209 Hutch? Took me a year to not put the N in there. So, okay, so we'll come in, we'll meet up on 5:30. Hopefully you guys can use the Slack page, but don't let that stop you from coming up with questions during the review session. If it's not interactive, it doesn't last very long. So if there's no questions, I don't have any answers, so I'll go to dinner. So one thing I don't love on review session is we get to the end, maybe around 7 o'clock, and sometimes as we get a little bit more comfortable with it, we'll go even longer, 7:30, and then at 7:30, I call up my wife and I say, hey, let's go to dinner. So we go to dinner right afterwards, and then 3 students come up to me right at the end and say, well, I've got 5 questions. And it's like, why didn't you ask during review session? It's like, I didn't feel like it. So just be aware that about 15 minutes before I think we're about to leave, I usually text my wife and tell her where I'm going to meet her. So if you make me wait an extra 45 minutes, I get in trouble for that. So just be aware. If there are things that you want to talk to me about after review session, I'll pad in about 10 minutes, because I know that there's sometimes some natural questions or something like that. But if you're intending to soak up an hour of my time right after we finish, I might say okay. But I never love that. Make sense? Cool. Okay, let's come back to joint order stats. So let's just finish that formula. But this is essentially where the formula comes from, is just this picture. I'll say a few things about it. So there's going to be the ith largest thing. There's going to be the jth largest thing. And we're going to give those some names. So I'm just going to denote the random variable at that position, and I'm going to call it U, and I'm going to call it V here. So that's what the book uses. So just as dummy argument for what is that position on the number line. So, and it takes on two different meanings to us. This is where xi lives, and this is where xj lives. So, right there. If you don't like thinking about the densities right away, we can do the same thing that we talked about in the one-dimensional order stat. If you're one of those epsiloners that likes to take limits and derive everything, you can say, forget about what happens at this instantaneous point. Let's just talk about the probability distribution of everything being in an interval right here. So I could consider some interval of length 2 epsilon. So I can just kind of build in that radius right here. I can do that too over here. And I'd let this be the exact same window length. And so that might be some skinny window. So now instead of talking about the density function at U and V, I could talk about the probability around U and V. So what I'll do at the end of this, and I'm not going to do it all formally, is I would just take the limit where epsilon drives down to 0. So what's the probability of everything being in here? It's not this, f of x u, but it's the probability associated with that. So what I mean by that is I would take this point right here, I would subtract off that point from the density function, and I would divide by 2 epsilon. And then I would scale everything, and I would take that derivative by taking that limit. So that's the formal justification. If you were trying to be rigorous about this formula, you would take that limit. But if you understand the connection between a density and a probability function, that should be almost immediate to you. So I can talk about the probability of all of the different points. If this is the ith largest thing, then I would think about over to the left of this, there's I minus 1 things over here. Each one of those happens with an actual probability. So that's going to be f of x, u. It's important when you're giving a lecture on this to say x before you say u. So this one is no problem. The complementary probability over here is 1 minus f x v. Right there. So things happen with probability, with that probability over here. If that's going to be the j largest thing, there's going to be n minus j things here. Those are actual probability statements about points being there. And I'll just draw a picture that there's some number of points here, and it's going to be j minus 1 minus I. We wrote it down a little bit differently last time, but there's j things up until there. We're not counting this one. So we're counting all the things over to the left-hand side of that. That's the j minus 1 things. And then I'm going to subtract off those I things. So I'm only talking about things in this interval. So you can write it down if you'd like j minus I minus 1. I get confused sometimes when I hear things and I'm thinking about it a little bit differently. Both are correct. So if I asked you for the joint distribution of 3-order statistics, you do something very similar, and you just count things up in the bins. And it's pretty easy to do. So you just come over to the right-hand endpoint, whatever order statistic that is, subtract off 1, and then subtract off everything to the next order statistic point. So this is that many things. And these happen with probability f x v minus f x u. So that's the probability of things being in there. So if I were going to end up producting together everything in this, I'd be describing a probability of something, and I would be talking about things being in this small window as well. And so if I took the limit on the left-hand side of that joint probability function, and I scaled everything to 2 epsilon, and I took the limit, then I would do everything to the right-hand side, and I would drive epsilon down to 0, and these things would converge to densities, and I'd be describing the joint density function. And that's what we really want to do. So if you want to take this picture and butter it up into something formal, you could do that. If you don't want to do that and you just like describing the picture, that's good enough for me. So in this class, I don't need you to be absolutely rigorous, but I do want you to get your calculus right. So we don't need measure theory in this class to do everything, and we don't need to be really pedantic. If you are interested in that sort of stuff, and you don't believe anything until you've gone through 17 proofs, and the proofs have to be absolutely correct, take measure theory or advanced inference, the 6,000 level versions of this sort of class. Measure theory will take you through all that stuff. So I don't think that in this class, this is where we want to be. Now, everybody has their own opinion. I'd rather give you tools and show you how to use this and how to practice as a statistician. I will be describing some theorems where it's like, it's interesting, and I think it's super interesting, but it doesn't help you to be a better statistician to know certain facts. So things like Basu's theorem, that shows up in chapter 6. So, does anybody know what that theorem says? Has anybody ever heard in a colloquium, like, is that statistic complete? Or anything like that? I've never heard that. So we will talk about it because it's interesting, like what are the properties of certain statistics? Has anybody heard anything like, okay, your probability is 0.82, I want to know how that converged. Did that converge almost surely? Or is that improbability? At some point as a practicing statistician, you might not care. There might be elements that help you to understand things if you have errors in code, and like, you know, whether or not things should be converging in certain ways, and we'll describe those, but I'm not going to turn this into a measure theory class. Okay, so if we're going to write down our joint density, I'm going to give us a little bit of notation. I'll call this xn, x1. So these should be bold to denote the random variable, but again, I don't really care about that. So it's just notation. And then I've got my dummy arguments. So this would be v and u. So for the actual arguments on the real number line. And then I just need to product together all of this stuff that I'm talking about. So when I described the picture, I said and a whole bunch of times. And every time I say and, I mean product. So if I think things are independent of each other, then I think product. I will point out that all of everything I'm saying again pertains to IID data. So when I'm describing all of this and I'm doing all the permutations, I'm assuming I don't really care if that's the 7th thing that I've seen or the 12th thing that I've seen in the actual sequence of random numbers that came out of the original distribution. So when I'm scrambling everything and I'm taking all my factorials and permuting everything, that's the IID assumption in there, that I'm just able to rearrange everything. If things were not IID, then I could just rearrange everything willy-nilly. So the original instances are IID. So how many different ways can I rearrange all of the data in there? N factorial, different ways. And now there's a whole bunch of rearrangements that I don't care about. I don't care to distinguish in these n factorial different permutations. And so permutations are coming through a product. So if I'm going to remove certain permutations that I don't care about, to remove them, we divide the possibilities. Hopefully they describe this very well to you in your probability class. Hopefully you've had a couple of those at this point. So how many different rearrangements are there of this stuff that I don't care to distinguish? I minus 1 factorial. How many different rearrangements here are there that I don't care to distinguish? It's that number of things factorial, so I'll write it out the other way. J minus I minus 1 factorial, and then there's n minus j factorial, different rearrangements that I don't care, they're all the same to me. But we have to count them all up. So that's the different number of rearrangements. And then I'm going to multiply it by something. Now, I usually circle my x's when I do this so that you don't see it as an x, a variable. I just mean multiplication. I don't mean a tensor product or anything like that. I guess you could call it a tensor product, but it's still just scalar. So I'm just multiplying. Yes.
The subscript should be ij, right? X and x, x and x1.
Where am I at? Where am I looking?
The function f subscript.
Oh, xn, x1, right here. You want me to go the other way?
I think it's why don't x I x g?
Oh, thank you. I'm ahead of myself. So J and I. Yeah, thank you. You know where we're going. Thank you. Important. Okay, now I want to just product together my density functions right here. I'm going to imagine I've taken that limit and induced those density functions. So this is going to be f of x, u times f of x, v. If you did add together all of these points in here, that number plus that number plus that number, that would be n minus 2 things. If we had n, if we were looking at three order statistics, we'd be adding things together until it's n minus 3. So if you just wanted to double check, where are the other two things in here? They're those points. So, and then I've got these probability functions that I need to multiply in. So times f of x u I minus 1. That's the probability for each one of those occurring there. And then I've got the number of rearrangements, the number of ways. And I've already accounted for that there. So times this probability, f of x, v minus f of x u. This is j minus I minus 1. And then I've got the complementary probability, f of x v to the n minus j. So, and that's my density function. I probably need to be polite and tell you there is a restriction on this, and I wrote that down over here, right here. But I can do it in terms of the random argument that u itself is less than or equal to v. So that's my dummy argument. So I should probably build that constraint in. If they're ties and all of that, all these formulas still work. So if everything is tied up. So these are exactly the same numbers. That's possible. It could happen. And so what I mean when I say ties is imagine n was something like 4. And I had x1 was this value. X2, let's say, was 2. X3 was 2. And x4 was 7. Something like that. These are ties. That's the second order stat. That's the third order stat. That's how you describe everything. So, do these formulas hold in cases where ties exist? Yes. Work out perfectly. No problem. So that's the joint density formula. And if I wanted to know what's the probability of u and v being in different ranges, I could integrate over those and come up with that cumulative. So the way we did it with the one-dimensional stuff is we built the cumulative first, then we derived the density function, but here we're going the other way around. So any higher order analysis of joint order statistics, you'll have to work through the density function if you can write it down. So, any questions? Pretty straightforward. If I asked you on a midterm, write down the formula for the joint order statistic for 17 order statistics, you could do it, right? It'd take you a long time. So I'd probably be able to gather whether or not you know this off of 3 order statistics. It's a very common question. So I would consider those free points at this point. So make sure you know how to do that. Okay, cool. Let's work through an example. Let's finally work through this example in the book. Of looking through the joint order statistics of these two things, the range and the mid-range. Why are we doing this? Why is this useful? It's just a mathematical exercise. I don't find any great importance about the joint distribution of these two things. I'd probably study that if I wanted to, but I'd never use that statistic for anything. It's just bizarre. So, but at the same time, it still makes for a nice calculus problem. So let's do it. So joint for R and the mid-range. The book uses V for mid-range, I just can't do it. So after years, I finally turned that into an M. For hopefully obvious reasons. Okay, so if I want to come up with a joint density, and we'll derive this density function. I usually say Dist, but you know what I mean by now. There's two steps involved. So what I would first do is I would come up with the joint for xn and x1, so the max and the min, and then I would transform those. So 2, transform. Transform with something with a one-to-one relationship. You can check real quickly, this is a one-to-one relationship between everything, and I'll also point out that the relationship is linear. So you can see that. There's no quadratics, there's no signs in there, there's no non-linear functions. The transform itself is linear. Let's just write down the formula real quickly for doing a transformation of variables in one dimension. So transformations. I'm not going to give you a full-blown lecture right now on transformations because I'm hoping that you remember this stuff. You know how to do it. It's almost instant to you. But if you want to practice problems, practice transforming some random variables. Some are hard, some are easy. So it's good to work through some hard ones and see what hard elements of problems are. But I'm not going to try to make anything too difficult on a midterm or something like that. So transformations in one dimension. So what we normally do is we might have some density function, xi's are coming from f of x. Right there, using our same notation. I don't really care if this is a scalar, if it's a vector, if it's something else. It could be any random variable to us. So don't really care. I'm calling it one-dimensional, but I'm just thinking of it as one argument. So this would scale up to multi-d stuff. If you wanted to transform, so let's say I ended up having y is equal to g of x. So that's some transformation. And I'll just make it real easy. I'm going to say that this transformation function is one-to-one. So if it's not one-to-one, what you need to do is break this function into partitions where you have one-to-one regions and do this analysis in each region. That can be difficult. So figuring out where the breakpoints are and everything, that's the part that can make this really difficult. I won't ask you any problems like that where you're trying to figure out where the breakpoint is to figure out where the one-to-one regions are. I will say, when I used to tutor, when I was a graduate student, I would pride myself on being able to do people's homework problems when they just came in and asked, and they came in with like a barrage of like, I don't know how to do this, blah, 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 blah. Settle down, you know, let's work through it patiently. Every once in a while I'd mess a problem up and say you have to come back tomorrow. And it would usually be on a problem like this where I wasn't in a one-to-one region and I'm like, this isn't integrating to one. So I'd always do the double check or something like that. So what would I normally do? I'd run back to my computer, simulate everything, you know, see, oh, I see that there's a change in everything. And you could kind of see that when we simulated all of this stuff and I drew a picture that looked like this. I'll label this picture a little bit more clearly in a moment, but this was the mid-range and the range. And when we simulated everything looked like that. I will point out, this is actually kind of convenient that it's like this and that the triangle isn't flipped the other way. So when the triangle is flipped the other way, then I have to break everything into a piecewise function. So you have to integrate over it. But this way, since we're defining the function in terms of r right here, I can integrate across just and then integrate between these two bounds. And I don't have to break the space apart. Okay, so I'm going to say it's 1-to-1. So that just means that I can, if you tell me what x is, I can tell you what y is. If you tell me what y is, I'll tell you what x is. So G inverse y is equal to x. And this is how we transform. So I'm going to write down this density function. This is going to be my new random variable. So f's not the same f, it's a different function. It's going to be an argument of something that kind of looks like a non-bolded version of that. So that's supposed to be bold, and that's just the argument on the number line. And all I do is I just take my original function right here, and I just, instead of writing x in here, I write down the name in terms of y. So they're one-to-one related to each other. So I just plug that thing in. I'm missing something in all of this. So it's a one-to-one relationship, and I just plug that thing in. You've got a name of it in terms of x, but I can re-describe it in terms of y. And they're ultimately describing the same things. So this isn't quite right because I've morphed the space when you do everything. So you kind of morph it. So if I'm going to integrate over things, I've taken the space and I've kind of morphed it, and the area in that space is not being preserved correctly. And so that's where this extra term comes in, dg inverse y dy. And I need to take an absolute value over it to make sure everything's positive. Can somebody tell me where that term really comes from? I've kind of described it intuitively as it's our stretch factor. And it's accounting for our morphing in our space, how much we've stretched it. There's probably a better explanation of where it comes from. Can anybody think of one?
If you're using the CDFs and looking at probabilities, then you can find the CDF, and then that term is coming from the chain rule.
That's it. So Jared understands this perfectly. So if you describe the probability transformation in terms of the CDF, the actual probability, and you're using this as your new random variable right here, when you take a derivative over everything, it's the chain rule. So when you take the derivative over everything, turning that CDF into a PDF, you get this dg inverse y dy term. That's the chain rule. Where does the absolute value sign come from? That kind of seems a little bit like a heuristic. It's like, so I could answer that, well, we know the thing needs to be positive, so we need to assure that it's positive. But mathematically, where is it coming from? Jared's still right, it's still a chain rule. That term will always be positive. So if I rearranged my bounds, you know, which way I was integrating from, and I was really specific in the CDF, when I took the chain rule, it would always turn out to be positive. So it's just a reflection of making sure you get this exactly right, that it does turn out to always be positive if you employ the chain rule directly. There's a problem in the book that I'll assign to you that it says if you have the minimum of 2 normal random variables and you square it, you're supposed to prove that it's chi-squared distributed. I will point out that's not true if you had 3 normal random variables, if you took the minimum and squared it. So some of you might know that a normal squared, a normal 0, 1 is a chi-squared, but it's not, that's not the argument. You actually have to go through the whole transformation, and you'll notice that in a 3-dimensional analysis, if you have 3 numbers, you took the minimum, squared it, it wouldn't be chi-squared anymore. And if you wanted to check that, you could simulate it like a GIF. So, but when I describe that problem to you, I'm going to work through what Jared just said explicitly to drive everything. So work through the probability function, take the derivative, show you what the chain rule is, and build up that transformation from scratch. So if you want a lesson on this, Stay tuned for that homework problem. I'll point it out to you again and we can cover it in a review session. Okay. So in higher dimensions, we do something kind of like this. So what we're going to do for our problem is we are going to we're going to look for f of r, and I'll be a little bit inconsistent and just use lower cases and upper cases so I don't have to bold. That's really hard for me to do with x's, but with r's and m's it's pretty simple. So I'm going to build this up. So what we're going to do is we're going to take our distribution on xn and x1, and I'll give us some notation. I'll just call it an xn right there and an x1 right there. Just make sure that you don't think of this as the original data points. They're the order statistics, so I'm giving us a little bit of notation to note that. I'm going to rewrite this as a function of r and m, and I'm going to do the same thing here. And I'm going to rewrite that density as a function of r and m. So when I see xn in this formula, I'll replace it with a equivalent function in terms of r and m, and I'm going to do the same thing here. And then I'm going to multiply by this Jacobian term. So in the one-dimensional case, I always call it a Jacobian too. So still say Jacobian. A lot of times when I write my derivatives, I write partial signs. And if it's in a 1D analysis, I don't care, it's still partial. So it doesn't really matter to me. I like to think just automatically in the higher dimensional representation. So if my language doesn't exactly match yours, it's because I'm always saying it in high B. So what is this Jacobian term? So there's lots of ways that you could formulate it. But again, I'm going to be writing down some function of maybe xn in terms of r and m, and I'm going to take a derivative with respect to one of the names of the transform random variable, dr. I just pick that automatically. So then I might do something like this, that this is dxn dm. As soon as I build my rule right here that I'm taking the derivative of this random variable with respect to r and this one m, I have to follow the same rule over here. So that's the only thing I have to be consistent about. If I took the derivative with respect to r here, I need to take the derivative with respect to r there. If I take the derivative with respect to m there, I need to take the derivative with respect to m there. And then I just do this with the other random variable that I'm transforming. So this is going to be x1 right here. I could reverse these columns and I could reverse that right there. It won't make any difference. Every time that you permute the columns and the rows, you're just changing everything up to a negative sign. If you do it twice, you change it by 2 negative signs, so that's positive. So that doesn't really matter. So we're always taking the absolute value over this. So again, just pick some order and then stick with that order. And if you get it wrong, it's because you didn't stick with the order. Probably got the derivatives right. Okay, so that's what we do here. Again, this is the same thing. This is that stretch factor right here. So this is the absolute value of a determinant. If you go back to your calculus class, at least this is the way I've read it in like 3 or 4 different calculus classes when they describe this. First, when they're teaching you about determinants, they probably taught you about finding areas in one of those parallel pipettes. So that shape. So it looks like a rhombus or something like that in high dimensions. So you can build the axes of the rhombus and then use those vectors and take the determinant over it. And they taught you that that was the area of that space. So the determinants are measuring areas of spaces. So if we go back to the intuitive explanation, this is our stretch factor, and it's just making sure the areas of the spaces correspond to that transformation. You have to do the exact same thing right here, where if this isn't a one-to-one transformation, if I can't come up with a one-to-one form right here, I'd have to break the space into lots of different regions. And in a high-dimensional problem, that would be hard. So figuring out all the bounds on everything would probably be really difficult. So could be arbitrarily difficult. Again, I won't give you anything that's just totally obnoxious on a midterm. So I don't want to grade you on necessarily how good your calculus is. I would rather stick with the statistical concepts. Okay, so let's just work through this. So first thing first is we need this function. So that's step one, and then we'll apply that formula to get the transform. Okay, so fx n and 1. I'll try to be consistent about my order right here. I very often switch it. So keep an eye on me. So we'll just apply that formula that we had before. It might be helpful if we keep this on the board for a second so we can stare at it. But eventually, if you're applying this, you'll probably write that out real quickly and just insert everything into it. So this is going to be n factorial. Right there, that's the easy part. The first bit, I minus 1 is 1 minus 1 because we're looking at the first order statistic. So 1 minus 1 factorial, I'll write it in so you can see where everything comes from. The j minus 1 minus I or j minus I minus 1, whichever way you want to think about it, that's going to be n, that's j right there, minus 1 minus 1. That's the first order statistic, and here's the other one. So that's n minus 2 factorial. And then our other thing, n minus j is n minus n in our case. So there's only one way you can do all of that stuff. So that's the number of rearrangements. And then we're going to have our density functions. So for our example that we've been studying, xi uniform, 0 to alpha, we know what the density function is, and we know what the CDF is. So f of x is just equal to 1 over alpha, and I probably should be polite and write down the bounds on all of this. X lives between 0 and alpha. Sometimes I forget to do that on the board, so always keep it in mind that until you write the bounds down, you haven't expressed the density function quite yet. So if it's totally obvious what it is, I won't mark you off on a midterm question or something like that. But if it's not totally obvious and it's part of the answer, then you might get marked off. So I always have it in mind to write down the bounds. So the cumulative, even I can do this integral here. This is going to be integral of that thing, 1 over alpha between 0 and x, dx, and that's x over alpha. So again, I've used my notation and recycled my x's a couple times, but you know what I'm talking about. So that's my cumulative function. I probably need to stick with the same bounds, but they haven't changed. So I've got two of these, 1 over alpha times 1 over alpha. So that's my two different density functions right there. And then I've got all of this other stuff. So I've got x1 over alpha to the 1 minus 1. That's going to go away. This is going to be xn minus x1 over alpha. This is raised to the n minus 2. That's that number of things. And then I've got the last bit, and I'll just write it down so you know where all my work is coming from. So this is going to be 1 minus xn over alpha. And this is going to be n minus n. So that goes away. And then I need to be polite and tell you where all this stuff lives. I need to tell you that x1 is less than or equal to xn. It's just by the nature of the problem. So this just reduces to this. N factorial over n minus 2 factorial. There's probably a nicer way to write that. So times 1 over alpha squared, that's these, but I want to just point out that these alphas right here, there's n minus 2 of those that I can factorize out with those ones. So if I wanted to just collect all of my alphas in one step, there's 2 of them in the denominator there, and there's n minus 2 coming from there that I can factorize out. So there's n of them in total. So xn minus x1 to the n minus 2, and everything else is just 1 in that equation. Again, we still have the same bounds. So not too hard. So coming up with the joint density of order statistics is a piece of cake if you know the formula. It's just plugging everything in. And I give you a couple problems that you can do that, and they have you work through some conditional distributions. I'm not going to check to see how well you simplified it. I'm just going to see that you took the joint and divided it by margin, and that there are the right equations in there. And so just exercises to work through all this stuff. A little bit more practice. Okay, now we just need to do this formula right here. So I need to re-express xn in terms of r and m, and x1 the same. So now I need to play around with these bounds a little bit more. And think about these things in terms of r and m. So let's think about our transformation. So r is equal to xn minus x1. And I'm going to redo the notation just so it matches what I've written down before. And I'm going to get rid of my braces, just because that's what I'm using right here. So hopefully you can stick with that notation for a second. Again, they're just dummy arguments. So, and then I have m, and I'm going to multiply this by 2. This is 2m is going to be xn plus x1. So before I took those 2 order statistics, divided by 2. So I'll multiply both sides by 2. And I'll just rewrite everything. So I'm going to do the same thing I've done since high school, and just work through this 2 different ways. If I add these 2 functions together, 2m plus r is going to be xn times 2. So I just added those 2 things together to get that. I could also subtract everything from each other, so I could do r minus 2m right here, and the xn's will cancel each other. And I'll wind up with minus x1 minus x1 again, so this is going to be equal to a minus x1 times 2. So that's just another way to express the exact same relationship. I'll write it over again one more time. So I'll just write that m, let me rewrite this in terms of n. And the reason I'm thinking about rewriting it in terms of n is that's what we put on our y-axis. So I always like to express everything in terms of what's written on the y-axis. You could do it in terms of the x-axis, and that would be fine too. So I've just kind of arbitrarily assigned one is the x-axis, one is the y-axis. So we'll stick with our picture that we already kind of have a mental map of. So it looks like this. M, R. We kind of know it's going to look like this, but we haven't really established this yet. So we're just going to keep that in mind. The reason I like to do it this way and not the other way is because I would have a piecewise discontinuity, or I'd have to describe it as a piecewise function. So, arbitrary choice. So, I like it this way because I can describe it as just one easy equation to write down, like this. So, let's just rewrite everything is m. So, I'll write down m is equal to xn minus r over 2. That happens here. So, I just rearrange that. And then I've also got a m is equal to x1 plus r over 2. So just a little bit of mental arithmetic. I think those are correct. That makes sense to me. Okay, so I've got these 2 formulas right here. And I know that they have this relationship between m and r, and I can describe the function of m as a function of r right here. There are constraints on all of this. So that might not be obviously described here. So r lives between 0 and alpha, but we notice that these need to be positive. They can't be negative, so you see that negative sign pop up right there. And you think there's a possibility this thing could go negative on me if we don't constrain the region of R. That's where these bounds are coming from. So that thing needs to be positive at all times. So the way I like to do this sort of problem, I was trying to think back to when I was in calculus class a long time ago. I used to be really good at this. And then I noticed after 10 years of grad school, 10 years as an assistant professor, I forgot how to do it all. So, but I've re-reminded myself how I did all this. Because I usually first think about the endpoints, the boundary points. I also think about the nature of the equations, and I know that it's linear in the equation, so I know the boundaries are described linearly. So what I usually would do is I would first think about m, and I would think about r, and I would just think about the extreme points in all of this. So I know that m can go between 0 and alpha, and I know that r can go between 0 and alpha. So I can think about when that happens right there, that the mid-range is actually alpha. That's when xn is equal to x1 is equal to alpha. And this happens down here when xn is equal to x1 is equal to 0. So that's where the mid-range obtains that right there. And then I usually think about how does the range obtain a value of alpha? And there's only one way to do that. So that's when xn is big and x1 is as small as it can get. And so there's only one way. This is xn is equal to alpha and x1 is equal to 0. So I think what I would normally do when I did these sort of problems is just think about the boundary conditions, what happens on all of those. If I had a computer right in front of me, I'll admit I'd probably be lazy and just simulate it real quick. But if I were taking a test, I couldn't do that. But if I were writing a paper and I wanted to make sure I could definitely do both, the math and the sim. So I know that these are linear equations, so if I were taking a test and I wanted to be really quick about this and I didn't have time to justify everything, I know they're linear, I know that these are the boundary conditions, and so I would know, bam, those are the lines. If you don't like that, we can be a little bit more formal about everything, and I could just think about what the extremes are on these equations right here. So I know that xn can get as big as alpha. So I could make this to the limit where that's alpha and just still think about it as a function of r. So this would be m is bounded by alpha minus r over 2. And boom, that's one of our lines right there. This is alpha minus r over 2. And then I would do the same thing here, and I would think the extreme on the minimum, which is bounding from the other side, can be as small as 0. So this is going to be, m is going to be greater or equal to the smallest value I can plug in right there, 0 plus r over 2, which is r over 2. That's that. So quick mental refresh back from freshman year or something like that. Hopefully you guys still remember how to do this stuff. So it's not going to go away anytime soon. So now all we have to do is just plug all this stuff in. So at least we have our bounds, and we'll keep those around. So there's one of our bounds, and here's our other bound. So we've expressed everything in terms of r just because it was easier to do that way. So there's arbitrary choices you can make that make your life easier, and we pick those. Why did we pick them that way? Because it makes the problem easier and also coincides with what the book did. So, okay. So now we're able to do the transformation. So let's just work through the Jacobian real quickly. We probably need to re-express everything in terms of, I'll just write these down. Xn is equal to m plus r over 2, and x1 is equal to m minus r over 2. It's the exact same thing that we wrote down over there. So those are strict. So I just rewrote this. So when we take our Jacobian, it's convenient to express everything that way. So I'm going to just say dxn, dm. I'll change the orders. I don't remember what I put down last time. So let's go dxn over dr. So I decided to be consistent in this direction, so I picked that direction to put everything, so now I need to follow the exact same rules in that direction. Before, when I described this, I went the other way. So again, there's no right or wrong way, you just have to be consistent. So as soon as you write down the first line, you know what you need to do for the rest of them. So this is going to be x1 dm. Why dm? Because that's the dm right there. And this is dx1 dm. These are pretty easy derivatives to take. Jake?
So the second m is supposed to be r.
Yeah. So like clockwork, say one thing, write the other. So yes, perfect. So dx1, dxn, dm, that's pretty easy. That's a 1. So with respect to r, that's a 1/2 over here. So the derivative of this one with respect to m is 1, and the derivative with respect to r over there is minus 1/2. So take my derivative, this, or take my, the determinant of this thing. This is just 1 times minus 1/2 minus 1 times 1/2. So this is 1, I'll just write down minus 1/2 minus 1/2 right there, and I set it up in such a way that this is negative. And if I would have permuted it, it would have been positive. So again, that was arbitrary. If you actually explicitly do what Jared said, it always turns out positive. So this is going to be minus 1/2 minus 1. Absolute value, that's 1. So that's kind of nice. That means that we didn't change the stretch on the space. So the area still means the exact same thing. And that's how I interpret that. So now we just need to complete the problem and plug everything in. So I think what we'll do next time when we come back is plug everything into this equation and see what everything is. So plugging in, we'll get F, R, M, R, and N. So next time we'll come back and we'll plug everything into that equation, see what it is, talk about maybe a few of the issues that the book talks about. They integrate everything, they'll integrate it over M, they'll integrate it over R and tell you 2 different distributions. I think all I'm going to do is integrate it over M because that's the easier one to do. If you integrate over R, then you have to split everything into 2 different regions. So I'm just going to integrate everything over M and then discuss what they say about beta distributions. That what you get is a scale of a beta. So I'm going to try to introduce you to a beta distribution, beta functions as well, and beta densities. So 3 different betas that are related but are different. So try to refresh on betas real quickly. Then the next thing we'll jump into is the CLT, the central limit theorem. We're going to need 2 things to do that lecture smoothly. We're going to need moment generating functions, properties of moment generating functions. So try to refresh on that real quickly, and Taylor's theorem. So we'll probably spend about a lecture just on the preliminaries of what Taylor's theorem actually says, what it doesn't say, and then how to use it to prove some version of the central limit theorem. I'll say more about that next time. There are deficiencies with that proof, so we can even talk about the deficiencies with that proof. Cool. Thanks, you guys. more general, but sometimes you do it the easy way first. So we'll wrap up on our conversation about the range and the mid-range. We'll look real quickly at the distribution of the range, and I just want to use it to introduce you to a beta distribution. You'll be using them soon. We'll do a case study where we explore different inferences from binomials, and in a Bayesian context, beta distributions come up very naturally out of that. So I'll show you a lot of different ways to do things soon. Then we're going to cut over to the central limit theorem. So this one still gets me. I still like this. So out of all the things in all of stats and math land, this is still a pretty good one. It's wildly abused, but it's still useful. So central limit theorem. I think you all know what it stands for. What does it say, just real quickly? We'll cut back into it and rephrase everything. But just, I want to know where you guys are at with this. What does the central limit theorem say? And I will be astonished if nobody knows. Obviously. Say it louder for us. So she said, sum of random variables has a normal distribution. I like it. That's almost the central limit theorem. It's definitely a bit abusive, but it's in the ballpark. It's good enough for conversation. So sum of the xi's is normally distributed. And sometimes people will do this and they'll divide the sum of the xi's by n, but it's just a rescaling of the problem. So rescaling normals are still normals. So a lot of people look at this thing, I goes from 1 to n right here, and they'll say that this is approximately normally distributed, and it's going to have some mean, and it's going to have some variance attached to it. So this is about how people use the central limit theorem. So this would be kind of a practical statement of it, but this isn't exactly what the central limit theorem says. We'll come back to this later and we'll write it down a little bit more formally, but a lot of times people will say, oh, I've got an average of things. Give this some notation, x bar n. I usually like to put the n there to remind us if we're going to take a limit over something, and it's in there. When is this? Okay, if we did write this out correctly, so I have n's on both sides, so if I take a limit on this, we might notice this goes to 0. So this is the touch of butchery that we have here. We probably need to fix that up if we want to explicitly take a limit so that we don't take a limit and take this to a normal with mean mu and variance 0. So we'll be a little bit more specific about it, but in an engineering sense, this is what people do. So x bar is normally distributed. So averages tend to be normally distributed. So there's some statement about rates, how fast this happens. It happens quickly. People use it pretty often. What is the condition, the one criterion for this to be true? Or the approximate statement to be approximately true? Independence. So people say independence. It turns out, in a lot of cases, you don't even need the independence, but we will prove it in the independent case. So in a lot of dependent cases, there are central limit theorems. So there's different versions of these on different cases, but we will study the IID case. It turns out it's not absolutely necessary, but we're not going to go into every little nuanced detail. You need an advanced class of inference, and they'll go through some of this nuance. So I've got some distribution F right here that I'm sampling, and we'll do it IID. We'll use that in our proof to make everything a little bit simpler. But it turns out the IID statement isn't critical, but we need to define what kind of dependencies we have. A lot of people still study CLTs. So almost sure convergence of the CLT, that's in fashion still. So being able to come up with actual proofs of that, it's not always true, but in some cases it converges almost surely, meaning that once it converges, it never pops out. We won't study that here. We're just going to study the distribution of it. All I want to say is that in distribution it converges. And the only reason that we're going to water it down so much is because as a practicing statistician, all we want are to be able to compute probabilities. And so regardless of how it converged, we're still going to compute a probability off of it, and all we need is a distribution. But there are other forms of this. So we'll stick with the IID thing, but not absolutely paramount, but there is something that's critical for the CLT to be true. Somebody help me out a little bit more.
Is it the finite variance?
It's the finite variance. So we need that this thing has to exist. Now writing it out kind of implies that, but we need finite variance. So sigma squared less than infinity, i.e. it exists. So when we write less than infinity, we mean that it's a number, it's out there. So the variance of f exists in the first place. Distributions that don't have a finite variance, we wouldn't see this property. And a good example of that is a quotient distribution. So I'll just point out real quickly, if f is equal to a quotient, and you might recognize these as T1 distributions. If you know what a T distribution is, they're T1s. So that's a Cauchy distribution. We'll come back to all of this. We're just saying a bunch of stuff so we can know where we're going. These are some of my favorite distributions, but they don't have finite variances. They don't even have finite expectations. If I showed you a histogram of them, you might be inclined to say, if you were narrowed in to where most of the mass is, you go, oh, it looks normal. And it kind of does, but the tails are totally different for normals. That's a big deal. So if you're trying to quantify uncertainties, the tails are where you're interested. I'll also point out, variances are wildly important. I tend to think that they're the most important thing in all of statistics. So maybe covariances, relationships between variables. There's other things that are important, but a lot of times we're inclined to think about the mean before anything else. I like to think about the variance first. So, and there's a lot of analyses that I can't compare exactly what's happening because they might be on slightly different shifted scales or something, so maybe the means are a little bit different. And so maybe you want to do a variance analysis. I'll give you an example. Probably about 15 years ago, 17 years ago, I wanted to write a paper on cyclists were dopers. And unfortunately, Lance Armstrong came out and he scooped me. So he went on Open Free and he's like, I admit, I already knew. So everybody I had ever talked to, at least 50% of them were like, no way, it's passed every drug test. So I wanted to look at some data on this and make a statement about it, not specifically about Lance, but more about just the field and what was happening. And I had a personal interest in this. So I wanted to look at things like famous climbs that have been done and tackled for 100 years. Anybody know any famous climbs in the Tour de France? Just curious. Alpe d'Huez is the one that I wanted to focus on. Mount Ventoux is another one, the Tourmalet is another one. But Alpe d'Huez, it shows up about every other year. And if they miss Alpe d'Huez, everybody's disappointed. So it's an epic climb. There's 3 different pathways up to the top of that thing. There's a whole bunch of different pathways up to the top, and sometimes they move the finish line a little bit. And so here's a stat that I was aware of. When Greg LeMond and Bernard Hinault in 1986 battled to the top of Alpe d'Huez, and they dropped everybody. Their time was 45 minutes on the climb. And now, you would be hard-pressed to find somebody that does it over 40 minutes. So it's like the best guys are 5 minutes is a long time. So that's not just a little bit of time. And people say, oh, our training's better, or our bikes are lighter. So from somebody that knows a steel bike versus a carbon bike, that's not 5 minutes. It really isn't. That's all in your head. So there's a little bit of time there. Maybe they reserve more energy or something like that. But when you've got the top 50 guys going sub 40, what's going on there? Now, you can't compare exactly the means of these things because they move the finish line. So the conditions are a little bit different, but maybe you could study the variability of everything. Or so maybe you could study, somebody way down on the list and see that that's getting bigger. or the time is getting faster for somebody that's way down on the placings. But you can do this for everybody, and essentially what you want to compare is the variability of everything. And so what you notice is that now all of a sudden the slow guys are right up there with the fast guys. So the differences are much smaller. So I think that's a good analysis of variance. So we want to remember variance is critically important. We will see examples where variances don't exist, so we need to say something probabilistically. So the uncertainty is important, the distribution. Another example is climate change, for example. So everybody's all fixated on the 2%, the 2 degrees, right? 2 degrees Celsius, we're going to be hosed. We already are. So don't worry about it. We're all doomed. So it's not that it's gotten 1 degree warmer. Nobody cares about that. So they care about the variability of everything. So the variability of the weather is important, not the 1 degree thing or 2 degrees. That's not the big deal. So anyway, variances are important. This is something you'll always want to kind of focus on and keep in your mind. Okay. We'll come back to CLT in a second. We'll clean up this statement and we'll try to prove what this statement is actually trying to say. Let's just remember this problem. Let's divide by 2. I think from last time we had this. From last time, we had, I'll just remind us the 2 different things that we wrote down. We first worked through this distribution. And this looks something like, let's see how good my memory is today. Alpha over n. This is going to be xn minus x1. Does anybody remember what the exponent is? I do remember. I'm working the math in my head. I'm looking at that joint order statistic formula and thinking about everything. This was the n minus 2 term. This was the thing in the interval. That's where we got that from. So the j order statistic distribution minus the ith order statistic. And then we had something like this. Xn is greater than x1. This is going to be bounded by alpha, and this is going to be bounded by 0. So that was our distribution there, and then we transformed everything. So transforming, we were able to come up with this. The distribution on R in N. We just worked through this thing, xn, x1, and then we multiplied by this Jacobian. But we took, instead of taking xn and x1, we took this thing right here and we redefined it in terms of R and M. So this was going to be M plus R over 2, and this one is M minus R over 2. I probably should be more polite and follow my notation. So we put in those things. So the Jacobian we worked through, this was 1. That was pretty easy to work through. And so it's just plugging everything into this equation. And so this looked like this. N times n minus 2 divided by alpha n. And then I plug everything into this and I see where the xn and the x1 pop up. So this just looks like m plus r over 2 minus m minus r over 2. Raised to the n over 2, and then we had some bounds on this. I'll just simplify this thing for us. I've done it again. R, little r. You can write it both ways. Just you want to be consistent. So is it the space of this thing, or is it the actual thing that you're computing?
I think last time we had n factorial over n minus 2 factorial.
Yeah, that's true. So,
Okay.
Yeah, that's what I meant to say. And then those are the same things. So n factorial over n minus 2 factorial n times n minus 2. Thanks for that. So this thing right here is just r over 2 minus a negative r over 2 is r. So that's just r to the n minus 2. Right here. The m's cancel each other. So let me just ask. This density says something about r. Does it say anything about m? Is there any information involved in m? Totally. It doesn't show up right there, but it's in the bounds. So r lives between 0 and alpha, and then m lives between alpha minus r over 2, and this is r over 2. So that's what we've done last time. That's that triangular shape. So there's definitely information about m and m. You have to stare at the bounds to see it. So that's what we had last time. Let's just work through this remaining part that the book goes through. They work through the distribution for m as well. It's a piecewise distribution. I have no great insights from that distribution, so if you want to look over it and practice your calculus, you can do it. You know, but if I wanted to know what is the distribution of the range, this is just the integral of the joint distribution. So I'll say r and m, r, m, and I'm going to integrate over r. And I'm going to integrate, over m. This is the number one mistake you could make in this class. If you integrate it over that thing, that shouldn't appear over on the left-hand side. It's gone. So what are we doing? We're averaging. We're averaging it out. So sometimes I say we're marginalizing it. But all I mean is I'm looking at what is the average behavior of r by averaging out over m. And we're going to do this over all of m. Right here, I usually write it like that, the whole world of m. And so we can just write this down more specifically. This is going to go from alpha minus r over 2 to r over 2, n minus 1 over alpha to the n, and then this is going to be r to the n minus 2 dm. That makes it really easy, so I'm willing to do this integral. So this is just going to be n times n minus 1 over alpha to the n and rn minus 2. And this is just going to be r over 2 minus alpha minus r over 2. I have this reversed. So I've got to integrate in the other directions, right? This is this line that's coming down. This is the negatively sloped one. So I better do this. Easy mistake to make. How can I tell that this isn't going to work out? I'm going to have something that's negative that shows up here. So this would be something that's easy to recognize if you check your work. So I'm just staring at this thing and going, uh-oh. So the r's are less than the alpha. So we got a problem. So we got to reverse this. Mental sanity checks. Alpha minus r over 2 minus r over 2. So this is just going to be equal to n minus 1, alpha to the n, r to the n minus 2, alpha minus r. R lives between 0 and alpha. And hopefully you get to a point soon where you go, that looks awfully familiar. So let me show you another distribution. that's related to this. And in some sense, they're equivalent to each other. We'll be using this distribution fairly regularly in this class. It'll at least come up in an upcoming project. But the beta distribution. It's a distribution that lives between 0 and 1. It's very common to model probabilities from a beta distribution. We'll see it soon in an actual example. But this looks like this. So I'll say the density function is going to be fz. I'll just give it a dummy variable name right in here. Actually, let me give it the more common name, p. And p lives between 0 and 1. And it has a couple parameters involved in it. So oftentimes you'll hear people call these hyperparameters, and if they do, you know they're a Bayesian. So you're using some Bayesian lingo. But there's parameters that underlie this distribution. We usually call them alpha and beta. So, and they're numbers that are going to live between 0 and infinity. Both of them are going to live there. So they don't go negative. So this looks like this. It looks like this part, and then there's going to be some normalizing constant. So this is the kernel. I'm going to use that word a lot in this class. This is the chunk of the distribution that tells me everything I need to know. It doesn't have all the miscellaneous normalizing constants. So it's the stuff that involves the random variable p. So this is p to the alpha minus 1, 1 minus p to the beta minus 1. And there's some normalizing constant involved in this. And all I have to do to find the normalizing constant is integrate over that thing, over the entire range between 0 and 1. And then divide by it. So it's going to look like this. Integral of, and maybe I should do it like this, integral inverse, so that I can divide this thing right here. So you divide by the sum of all of it. This will just look like this. P to the alpha minus 1, 1 minus p to the beta minus 1. dt lives between 0 and 1. That's a definite integral. Does anybody know what we call this function? You know. Yeah, you're on. So this is the beta function. So that's the beta function. So I'll just point out a couple things. We've got a beta distribution, which is the cumulative over the beta density. It involves two parameters. One of them we call beta. And the normalizing constant is a beta function. Those are all different. They're related to each other. So lots of betas come up in this terminology. So we'll just call this beta, and it's a function of these two things, alpha and beta. So usually this is our notation right here. It has a relationship to gamma functions. I bet you know what it is. So, good. Does anybody else know how I write this out in terms of gamma functions? Good things for first year graduate students in statistics to just know off the top of their head. Stuff that comes in useful. Of course you can look it up if you ever forget. So once you get past the first year of school, then Wikipedia is your friend. Yeah, please, Jake.
I think it's gamma of A, gamma of B over gamma of B plus B, or it's the inverse of
Yeah,
that.
exactly. You got it right. So I think that I would be exactly at that same point. It's either that or it's the inverse of that. And I would have to figure out real quickly which one is bigger, the numerator or the denominator. So keep in mind, this has something to do with something living between zeros and ones. So which one is bigger? This thing grows faster than those things right there. So gamma functions have something to do with factorials. So I'll just point out gamma, and I guess I'll use my z right here. let's just say that's an integer. This has something to do with factorials. Somebody tell me what is the function in terms of factorials if z is an integer? Z minus 1, yeah. It'd be easy to do the z plus 1 thing, and I see that a lot. So, but it's z minus 1 factorial, right there. So when I come back and I look at this, I notice that this kind of looks like a gamma function, or a beta density, sorry. Except that's not a 1 right there. And these don't live between 0 and 1, the R, but it's just a rescaled version of it. So it's a rescaling of everything right here. So let's just put this into beta form if we were to transform and rescale the problem. So if I take this and I transform it, and the transform that I'm going to use is I'm going to say P is equal to R divided by alpha. So now this thing lives between 0 and 1. So now it has the same look and feel as the other problem. So if we're going to transform and I want to find this distribution on P, and I've got my distribution on R, that's this, right here, then I know how to do this. FR, R, and I'm going to need my Jacobian term. And in our case, it's just thing. Remember, it's a function of P, and so this is going to be a function of P the way that we write it out, so it's going to have something to do with P's in there. So R is equal to P times alpha. So if I just rescale everything everywhere I see an R, right here, I'm going to plug in P times alpha, and then I'm going to work through this derivative. What is this part? Real quick. It's alpha. Very good. So quick derivatives. So just alpha. So you just multiply that on both sides and take that derivative, piece of cake. And this thing right here is going to look like n times n minus 1 over alpha to the n. I'm going to do my substitution. So this is going to be P times alpha raised to the n minus 2. Then I'm going to have alpha minus P times alpha. There's only one of those. And then I've got my Jacobian term. It's that thing. That's that alpha. How many alphas are in here? There's n minus 2 of them there that I can factorize out. There's one of them here that I can factorize out. And then I have one more right here. So they all cancel right there. So this is going to look like n times n minus 1 times P to the n minus 2, 1 minus P, and we're done. And P lives between 0 and 1. Just to finish up the problem. You could check real quickly if you'd like to. You're going to invert this thing because that's the normalizing constant on the inverted scale. And you can figure out that that has something to do with factorials, and it's exactly this. So I'll leave that little algebra piece to you. You just work through those gamma functions and see that that's exactly this thing. So this looks like the kernel of a beta. Question is which beta is it? So usually we want to be really polite and say not just that it's a beta, but it's a particular beta. N minus 1. And 2. Yeah, exactly. So if you'd like, you can plus 1 minus 1 here, and then take plus 1, 2 minus 1. So this is just the same as 2 minus 1, so that's our beta term. So now you know exactly which alpha and beta to plug into this formula right here to get the n times n minus 1. It's correct, so I'll just leave it to you to finish up that detail. So these are betas. We'll come back to these later. So remember those. Any questions before we move on to CLT? We won't be able to finish this. We'll see how far we get on the preliminaries. There's two things that are involved in this proof in the book. There's Taylor's theorem and there are moment generating functions. So we probably need to just make sure that we're honed on both of those. So CLT preliminaries are, one, we better understand what Taylor told us. Taylor's theorem and Taylor's series. Specifically, they're doing the 1 with 0 that people call them in Lorentz series, but you usually only hear that out of freshmen in calculus. Usually everybody else just says Taylor. So we'll do it in a more general case, but we'll outline the proof centering everything at 0, but we probably want to talk about that centering. And then we also need MGFs. Moment generating functions. You'll want to be aware of all the steps of this proof, and you'll want to treat the remainder properly. So if I'm giving you a midterm or a final, I don't need the answer just written down. I want to see that you can justify whether or not the remainder is doing the right thing and not exploding on you, and you're going through all the technical details. If you do just write down the answer, and you're like, boom, the remainder I know goes to 0. I don't need to think about it. It always goes to 0 in all my classes. So I will give you a lot of your points. But if you take a qualifying exam in statistics and you do that, I'm going to take off a lot of points. So it kind of depends on what we're actually testing. So if you're preparing for a QE, make sure that you're thinking about all the nuanced steps and what the actual underlying theory is. So if I sometimes wave my hand a little bit and say close enough, that might be good enough for this class, but I want you to take it to the next level if you're taking a qualifying exam. If you're thinking I just want master's level knowledge of statistics, then maybe it's okay to say I know the remainder goes to 0. So just kind of depending on how far you want to go with this. Okay, Taylor series. Let me just ask you guys to see where you're at. What does Taylor's theorem say? Let's start with that. Real quick. Piece of cake, right? Do you guys remember off the top of your head? Are we ready to just fly through this, or do we need a minute?
Need a minute.
Need a minute. Okay, that's good. Same thing? Cool. Need a minute. Taylor's theorem says something like this. Let's just think about a just arbitrary function. So my f right here can be anything. It's not a probability density. It's not an MGF yet. Later on, we'll apply Taylor's to the MGF, and that'll be part of our proof. But sometimes this is true. So some k goes from 0 to infinity. I can write down x minus c to the k right here, and then there's some leading terms right here. These are going to be the k derivatives of our function centered at c, and I'm going to divide by k factorial. So that's my leading coefficient right here. Hopefully you recognize this. So this is not what Taylor's theorem says, but it kind of, when I was taking calculus, I kind of just thought about it this way. And then maybe you truncate, and now I'm a little bit more respectful about the remainder.
Isn't Taylor series?
Yeah, that's a Taylor series.
So what's the Taylor term?
Huh? Taylor's theorem? Let's talk about it real quick. So this is a Taylor series. They're related to each other. So Yeah, it's a Taylor series, but Taylor's theorem, Taylor didn't just say that. He said something else. What did Taylor actually say?
Estimation, approximation.
Yeah, it says a little bit more about an approximation. So most people don't use this because that's a bit cumbersome. So what they usually do is they truncate. They'll take this up to some finite, start that at 0, some finite number, and they'll plug this thing in, fk, centered somewhere. K factorial, x minus c to the k. So usually we truncate this thing. And that's our finite approximation to this function. But this isn't all Taylor said. He said something a little bit more than this. Taylor's theorem is a statement about the remainder. So what's really nice about this is that in this approximation right here, I get a better approximation if I keep incrementing this up. So Taylor told us that I don't need the 117th term. I wouldn't use the first, second term, third term, and then the 117th term, because the fourth term has more information from that. And so there's kind of a descending effect of how well we're approximating everything as we start adding in terms. So there's diminishing return in all of this. And so what Taylor said is that air, and we know what the remainder looks like. The air term is this. K goes from cap k plus 1 off to infinity. Fk evaluated at c divided by k factorial, x minus ck. He said you don't need to analyze this whole infinite series to understand the air. All you need to do is understand the next biggest term. So the air is bounded by this, cap k plus 1, c, divided by cap k plus 1, factorial, x minus c, cap k plus 1. So the airs are bounded by this term. So what it means is that the air is bounded by the lowest order term in the remainder. That's kind of nice. So he was able to show that as you keep adding more things, you approximate a little bit better, but that's going down. The amount of improvement is going down at each step as you start adding things in. So that's what Taylor's theorem specifically says, and maybe that's intuitive to us. That's nice, I believe you. So it kind of makes sense, I kind of get that. Probably start with like the linear trend and then add a little bit of bending, but after a while, you know, we're not adding too much to everything. Of course, this is an approximation that's good around C. In fact, it's perfect right at C. So, and we could see that. So the first term in this, the F0 term is no derivative in there. And so all the terms that are powered up to something that's different from 0 right here, they're going to go to 0 when I evaluate it at C. So it's going to be a perfect estimator at C. And then around it, there's going to be some air. And we could analyze how much air we have by looking at this term. More specifically, what we'll do, and we're going to do this in this problem, is we're going to compare the largest order term in our approximation to the smallest order term in the remainder. So, and if that thing blows up, then what that means is that if it blows up, if the remainder is on top or something like that, and the smallest order term is on the bottom, and I take a limit, if that thing explodes off to infinity, then it means there's too much going on in the remainder. And so if you think back to your calculus class, they told you about the radius of convergence. That you're looking at this term compared to the cap k term, and you're seeing where that thing is bounded. So usually, we'll do this.
What is meant by bounded here?
Doesn't go to infinity. Goes to a finite number. So actually we want things to go down to 0. So in a limit. So what we're going to do is we're going to look at f cap k plus 1 c times x minus c to the cap k plus 1 divided by f. Oh, there's a factorial in here. 1 over cap k plus 1 factorial. We don't really need to worry about this term because it's never blowing up right here. So cap k, c, x minus c, k, just k. So we're going to look at this term right here. So this is the remainder. It's what's bounding everything. And this is the largest order term in the approximation. Now, we probably need to check things like what they probably had to do in calculus is if you start moving away from C, how far can you move from C before that thing blows up? If that thing is blowing up and diverging, then there's too much in the remainder. So we're going to do it a little bit different, and we'll analyze things as a function of n and make sure that this term doesn't blow up as a function of n, and it actually goes down towards 0. So as a function of n, when we apply all of this, we're going to want this term to go towards 0. And it basically means that the remainder isn't overriding the approximation. That's what Taylor's theorem said. So engineers, probably okay if you're just right there. But make sure your approximation is good. I used to say things like, I never use Taylor's except for when I'm proving stuff. Nobody ever does this. And then I've had engineers come back and say, we use it all the time. So we practically use this. So I've never used it for anything too practical. But when we get into the delta method, it's applied there as well, and they're going to be applying the exact same stuff in the delta method. So if you don't catch on in this analysis what's coming up, the delta method will have a very similar analysis. So we'll be repeating this in the context of an actual approximation that uses Taylor's theorem. Later on in this class, you can tell me whether or not you like that method. So it's not my favorite, but it can work okay. Okay. Do we remember why the coefficients look like this? So the coefs are f, k, centered somewhere divided by k factorial. So for our polynomials. So Taylor series are polynomial approximations of things, and those are the coefficients. Could you derive that real quickly? Or a little bit more? I love this one when I first saw it in calculus because I was like, if you ever forget this, it's pretty easy to derive. Let's just do a couple of these terms, make sure we understand this. So f of x is going to be approximately some polynomial. I'll give my coefficients this notation right here. X minus c to the first power plus alpha 2, x minus c to the second power plus some coefficient x minus c to the third power, so on and so forth. So if I evaluate everything at c, so f0 c, that means that I didn't do anything to the function. It's still f. They're synonyms to each other. If I plug in c, all of the terms that involve the polynomial stuff, they have the x's, they go to 0. So this is just alpha 0. So our first term is the 0th derivative, and you can think of this as dividing by 0 factorial, but that's just another name for 1. You can leave that thing out. Let's take a derivative. F, our first derivative, I'll just denote it like that, usually we put a prime or something. X, so I take a derivative, that thing goes to 0 right here. So this is going to be alpha. So I take a derivative over x, all of this stuff goes to 0. So this is just going to be the alpha 1 right here, plus 2 times alpha 2 x minus c to the first power, plus 3 times alpha 3 x minus c to the second power, so on and so forth. So if I evaluate this thing at c, f1, at c, that term goes to 0, that term goes to 0, you can use your imagination, all the rest of them do too. So that's equal to alpha 1. So that's our first coefficient, our linear coefficient in Taylor's approximation. If I look at a second derivative, I'll just look at this and do the same thing. That goes to 0. When I take the derivative, that thing comes down. So this is 2 times 1 times alpha 2. All that other stuff disappears. Plus 3 times, I take a derivative here, times 2 times x minus c. This becomes linear, so on and so forth. So you'll notice that this is starting to look like 3 factorial. There's your 2 factorial. So if I plug in c, f2 evaluated at c, it's going to be 2 factorial times alpha 2. So our second term in our thing is going to be f2 evaluated at our centering parameter divided by 2 factorial. And I think you can use your imagination and do it one more time and see that 3 factorial evolving and where all the other factorials are coming from. So in general, the coefficients just look like this. Fk evaluated at our centering parameter divided by k factorial. So same sort of analysis. And I kind of like that. The first time I saw this, I was like, I can do that. So it took me a little while to figure out what was going on with the remainder. Okay, we know what Taylor's series are, and we know we need to be aware of the remainder. It'll be more formal next time when we apply all this to the CLT. Let's just look real quickly at moment generating functions. I know we're right about to go over, so I'll save this stuff for the very next time. But just as a reminder, MGFs, so I'll imagine I've got something coming from F right here. So I've got some X's, some random variable. Actually, I'll just make it a Y, since we're going to move over to that in just a second. So Y comes from some F's right in here. So the MGF is just this thing. The expected value of e to the yt. Usually we call this myt. M for moment generating function, there's our random variable, and there's a dummy argument right in here, t. So these are always a function of t, right here. What is this specifically? It's e to the yt, fy, probably want to be specific, dy. And we're going to integrate over all of y. So this is not a function of y, but it's a function of t. And what happens with these, if we take derivatives over them, they induce the moments of the distribution. We'll come back next time, look at what these things do, but I'm just curious, does anybody have a different name for this transformation? Has anybody ever seen this before? These are called Laplace transforms in other fields. So this is the Laplace transform. So if you take it a differential equation class, maybe you're familiar with those. There's something similar where I can put an imaginary thing right there. It's called the characteristic function in statistics. We'll talk about it ever so briefly at the end of this conversation. Does anybody know of another name for the characteristic function? It's the Fourier transform. So these things that we're using, we have different names for, but they're the same things that other people use, and we use them for slightly different reasons. But they're all very connected to each other. So let's come back next time, make sure we understand properties of MGFs, and then we'll start putting this thing together and try to prove that original statement that we wrote down, or something like it. And we need to write down explicitly what we're trying to prove. And then we'll apply all this stuff. This is one of my favorite things to test people on, so make sure you understand how all this works. Perfect. Thanks, you guys. Oh, also one more thing. Review session tonight, 5:30 in this room. If you have homework questions or other conversations that you want to have, it's a good time to do it. So it's better when you guys show up. Thanks, y'all.